In this video, we will discuss how a pore size resolved sorption isotherm can be measured by NMR. This work was done mostly by Agatha Gajewicz, University of Surrey. In this video, we will learn about how a sorption isotherm can be measured by NMR, how the effects of the changes in relative humidity on the pore space can be quantified, and we will learn about different filling mechanisms of pores during drying and rewetting of cement. The details of the experimental protocol are given in Agatha Gajewicz's thesis, chapter 4. The important points are: the samples investigated were made of white cement. In all cases, the water-to-cement ratio was 0.4, and before the sorption experiments, the samples were cured in Portlandite solution for 28 days. We have already discussed how simple an NMR experiment is to perform in the video NMR-I, how to perform the experiment. We consider a classic sorption experiment before we see how NMR can be used to elucidate the interactions between cement paste and water. For a sorption experiment, we need a cement sample, weight scales, and a suitable climate chamber, which can expose the sample to a controlled relative humidity. The sample is weighed, inserted into the climate chamber, left there, moved back to the weight scales. This is repeated until the sample has reached a constant weight. Today, this very simple process is often replaced by an automatic device which has the scales integrated into the climate chamber. Typically, one starts with a sample of high water content, which is then progressively dried, which is also referred to as first drying. Subsequently, these samples are exposed to higher relative humidity again, which is referred to as first absorption. In this video, the samples are then dried again, and this is a second desorption. If we do this, we obtain a conventional sorption isotherm plot. On the x-axis, the relative humidity is plotted, and on the y-axis, the relative sample mass. The black dots mark first drying, the red dots first rewetting, and the green dots second drying. Hysteresis is observed between 10% and 80% relative humidity. If we now insert the equilibrated sample into a suitable NMR machine, we can characterize the state of water in the sample. Let's plot the total intensity of the NMR signal first. The total intensity is proportional to the total water content of the sample. In this graph, we plot the total intensity of the NMR signal against the relative humidity the sample was equilibrated with. Here is the first desorption in black, first absorption in red, and second desorption in green. We note that in all cases, the curves have an almost identical shape to the curves obtained with the conventional measurement. This is expected since the NMR signal is proportional to the water content of the sample. Let's look at the extra information we can obtain by NMR in the next slide. On this slide, we consider the first desorption isotherm and how it is resolved in individual isotherms for each water population in the sample. In the video NMR-I, how to do the experiment, we have already shown how the total NMR signal can be split up into a spectrum like this. This example spectrum is a relatively mature sample equilibrated at 100% relative humidity. The peaks observed in the spectrum are caused by hydrogens in different environments. The first peak can be attributed to those hydrogens bound in crystalline hydrates. We assume that for the white cement used here, these are only ettringite and portlandite. The second peak can be attributed to the interlay of water. This is water located between tobermorite-like sheets in CSH. Its relaxation time is short, since the water relaxation time in NMR depends on the mobility of the hydrogens, which is low in this highly confined environment with a characteristic size of about a nanometer. The third peaks represent the gel pores. These are larger cavities with a characteristic size of about 3 nanometers located in defects between sheets within CSH. The fourth peak describes the interhydrate pores. These are larger pores located between stacks of sheets. So not within the CSH, but between larger groups of CSH. These pores are the remnants of the gel pores as hydration progresses. They are explained in greater detail in the video NMR-IV, time-resolved hydration. The fifth peak is water in larger pores, such as capillary pores and air voids. In this video, these two populations are grouped together and considered as larger pores. Two further definitions are important. We will talk about intensity in this video. Intensity refers to the area under a peak. For example, the intensity of the solids is the area marked in the graph. It is also important to remember that the signal intensity is proportional to the water content. Therefore, we normalize the total signal intensity to 1. This equates the signal fraction with the fractions of water in the sample associated with certain peaks. When we perform a sorption experiment and take an NMR measurement at each equilibrium point, the spectrum changes. We now see the schematic of a spectrum of a sample dried from 100% relative humidity to 48%. The main observations are: first, the solid peak has not changed. Second, the interlayer peak gains intensity but remains at the same relaxation time. Third, the gel pore peak shrinks in height and width and moves towards shorter relaxation time. And fourth, the two peaks for water in larger cavities have totally disappeared. For the successive analysis, please remember that the relaxation time of water in a filled pore is interpreted as being proportional to the pore size. Therefore, a shift of population towards shorter T2 indicates that the average pore size has decreased. A change in width of the peak shows that the pore size distribution changes. In case of the green gel pore peak, it is apparent that the left onset of the peak has not changed, whilst the right onset has moved towards shorter relaxation times. This indicates that larger gel pores have emptied. We will come back to this later. When the sample is dried further, we see that the intensity of the solid peak increases, whilst only residual peaks for gel and interlayer remain at a relative humidity of 3%. The large amount of information contained in these spectra can be better investigated in two separated plots. In the first plot, we plot the signal intensity against the relative humidity the sample was equilibrated with. The intensity is now normalized to a sample which is fully saturated with water. The black line is the total water content as measured by NMR. You have seen this line already on the previous slide. It is the NMR measured desorption isotherm. However, since we have now access to the spectrum of relaxation times, we can now plot the first desorption isotherm of each pore population individually by plotting the intensity of the peaks. Here is the desorption isotherm for the solids in orange, which remains almost constant. In red, the interlayer intensity is plotted, which appears to be constant down to 20% relative humidity. In green, we have the intensity of the gel pores, which gradually empty about most of the relative humidity range. And finally, we have the intensity of the water in large pores in blue, which empty during drying from 100% to 90% relative humidity. Note that the color code agrees with the left graph, which also acts as a legend. However, the analysis will be simplified by replotting this graph. We now change the relative humidity against the normalized water content in the sample. If the sample is at 100% RH, it is 1, and as water is removed, it decreases. At the upper x-axis, we retain the relative humidity scale. In black, we show again the total water content. Since the NMR signal is proportional to it, it is on the diagonal of the plot. We again plot the intensity of the solids in orange, which appears now to increase slightly towards lower water contents. The interlayer water intensity curve has now a much more distinct shape, as has the curve of the gel pores. On the second graph, we plot the T2 relaxation times associated with the gel and interlayer water against the water content. Remember, the T2 time of a water population is a measure for the pore size. The dotted lines indicate the lower and upper limits of the peak, so essentially the width of the peak. As before, in red, we show the interlayer water population, and its peak width is represented by the red dotted lines. In green, we show the gel pore population, and again the peak width is indicated by the green dotted lines. We now hide the curves and investigate how they develop during drying of the sample. During the removal of the first 10% of the water in the sample, the large pores empty totally. This is not surprising due to the Kelvin equation shown on the blackboard below the graph. The Kelvin equation describes how confined water suffers a depression of equilibrium vapor pressure as a function of the pore size. In other words, the critical radius computed from the Kelvin equation shows the smallest pores which are emptied at a given relative humidity. For 90%, this is 10 nanometer, so all pores larger than these values have emptied by now. The intensity of the hydrogens bound in the solids has remained constant, whilst the gel pore population has decreased slightly. Despite some water loss of the gel pores, the relaxation time, both width and position, has barely been affected so far. The interlayer intensity has slightly increased, but without any significant changes in the T2 relaxation time. If we remove about 40% of the water, the trends observed previously continue. The gel pore intensity decreases, the interlayer intensity increases, the intensity of the solids remains constant. Considering the T2 relaxation times, one notices now a decrease of the mean relaxation time of the gel pore peak. Also, the peak boundaries have changed. The upper boundary has moved towards smaller relaxation times, whilst the lower boundary has remained constant. This indicates that larger pores empty first. Further drying leads to new trends. The gel pore population remains almost constant at the residual level, whilst the relaxation time continues decreasing. The peak boundaries also shift to lower values. The intensity of the interlayer pores decreases now. At the same time, the intensity of the solids increases. The last data point was obtained by oven drying the sample. All pores are empty now, and the solid intensity has reached the value previous to its increase during drying. This behavior, which is quite unexpected, can be explained by a simple two-dimensional model of a gel pore. In Agatha Gajewicz's thesis, it is described how this model can even be made quantitative. We consider a filled single gel pore with a width within the size range of gel pores. The pore is located between two tobermory-like sheets of CSH. The water molecules are labeled green since they are seen as gel pore water by the NMR. We assume emptying via receding meniscus mechanism, leaving behind a monolayer of water covering the surface of the sheets as shown. This surface layer has a reduced mobility, thus it has a shorter T2 relaxation time. This relaxation time is in the same range as the interlayer water, which makes the NMR seeing it as interlayer water. Therefore, it is labeled in red. This leads to an increase of the interlayer water intensity. This monolayer water is likely to be less mobile than the interlayer water, thus it has a slightly lower T2 relaxation time, leading to a shift of the interlayer relaxation time towards shorter times. As the sample is dried further, even this residual layer of water is removed together with the water from the interlayer pore space. Therefore, the intensity of the interlayer peak decreases. As the surface of the CSH sheet is vacated by water, it is likely that O- groups belonging to silica tetrahedra at the surface of the tobermory-like layers remain protonated. These hydrogens have a very low mobility and are therefore seen as solids by NMR. This explains the increase in the solid intensity. We can apply the same analysis also to rebetting. So now we are talking about the first adsorption isotherm. We start at a sample equilibrated with 3% relative humidity. We again have two graphs. In the first graph, the relative water mass is plotted against the normalized signal intensity for each of the water populations we can identify by NMR. These are the total water intensity in black, the intensity of the solid peak in orange, the interlayer peak in red, the gel pore peak in green, and the intensity associated with the water in capillary pores, interhydral pores, and other larger cavities in blue. In the second graph, we again consider the T2 relaxation time, or the effective pore size. It is plotted against the normalized water mass in the sample. The red graph represents the center of the interlayer peak, the green graph of the gel pore peak, and the dotted lines again represent the width of these peaks. As before, we investigate the development of the pore spaces step by step. A residual population of gel pores, green, has remained at drying till 3% relative humidity. No water in larger pores such as interhydrate or capillary pores can be detected at this point. Increasing the relative humidity leads to further water adsorption. We observe now that the interlayer intensity, in red, increases while the solid intensity, in orange, decreases. This is reverse to what we observed during drying. The T2 relaxation times behave comparably. Relaxation time of the interlayer increases, as does the relaxation time of the gel pores. As adsorption continues, the interlayer intensity, red, decreases again, while the gel pore intensity increases. The solid intensity, orange, decreases only slightly. In this region, the relaxation times of gel, green, and interlayer, red, pores remains approximately constant. Towards the end of the investigated humidity range, the gel pores, green, intensity increase slows down, whilst the interlayer and solid intensities have become constant. This suggests that the interlayer pore system has now been filled completely, and only the largest gel pores are still being filled, at approximately 72% relative humidity. Therefore, we see an increase of the T2 relaxation time and a shift of the upper boundary of the peak of the gel pores. Similar to the process during desorption, we can attempt to explain these curves with a simple model of a filling gel pore. At 3% relative humidity, we assume that the gel pores are essentially empty. We do not understand the residual gel water signal yet, as previously mentioned. The model of the gel pore is again a slit pore located between two sheets of CSH. As the relative humidity increases, the surface of the empty gel pore is covered by a monolayer of water first. This has two effects. As we have already proposed previously, this monolayer is seen as interlayer water by the NMR and therefore shown in red. This leads to an increase of the interlayer water population. Before the surfaces are covered by the monolayer, they are, however, not bare of hydrogen. Hydroxyl groups as part of silica tetrahedra covering the surface are attributed to the solid signal. As the surface is covered by water, these are seen by NMR as part of the interlayer water. Therefore, the solid signal decreases as the surfaces of the gel pores are covered by a monolayer of water. We have seen that as the gel pores progressively fill up, the interlayer intensity decreases slightly. However, the gel pore intensity continues increasing whilst the interlayer intensity remains constant. This is different to the observations during first desorption, where the drying of the gel pores led to a progressive increase in the intensity of the interlayer. Thus, the further mechanism of pore filling is likely not to be just a reversed one, but likely to be different. The most likely scenario is that a second layer of water molecules adsorbs on the first monolayer of water, so the adsorbed layer becomes thicker and thicker. Eventually, this layer will become mobile enough not to be seen as interlayer water, but as gel pore water by NMR. Therefore, we change the color of the bilayer to green. This leads to a decrease of the interlayer water population during the initial gel pore filling, but not during the whole filling of the gel pores. This process can also be modeled quantitatively as described in Agata Gajewicz's thesis, but she and her supervisor are less secure about the validity of this mechanism than they are about the mechanism during drying.